14 billion miles from home, humanity's most distant spacecraft ran straight into something that should not have been survivable. Temperatures spiking past 50,000 degrees. A wall of energy so intense that scientists nicknamed it, quite literally, the Wall of Fire. And Voyager 1 flew right through it and kept going. Stick around, because I'm about to walk you through exactly what this boundary is, why it nearly defies belief that a 50-year-old spacecraft survived crossing it, and what both Voyager probes have found on the other side, in a region of space no human-made object had ever reached before them. And hit subscribe now, because this channel breaks down real published research without the exaggeration, and you do not want to miss where this story actually goes. To understand why anyone would call a region of space a wall of fire, you first have to understand exactly what our solar system actually is, because it is a lot bigger and a lot stranger at the edges than most people picture. Most of us think of the solar system as ending somewhere out past the last planet, wherever Neptune happens to be on a given day. But that is not how scientists actually define the boundary. The sun does not just produce light and heat. It also constantly sprays out a stream of charged particles called the solar wind, electrons and protons blasted outward from the sun's surface in every direction, all the time. That stream travels outward past every planet in the solar system, past the orbit of Pluto. It keeps going, carving out an enormous, roughly teardrop-shaped bubble in space called the heliosphere. Everything inside that bubble, every planet, every moon, every asteroid, exists inside the sun's direct sphere of influence. The true edge of the solar system, by this definition, is not a planet at all. It is the outer skin of that bubble, the place where the sun's outward-pushing solar wind finally runs out of strength and gets stopped by the pressure of the interstellar medium, the thin soup of gas and charged particles that fills the space between stars. That precise boundary has a name. Scientists call it the heliopause. For decades, the heliopause existed only as a theoretical line on a diagram, something scientists calculated should exist based on physics, but had never actually measured directly because nothing humanity had ever built had traveled far enough to reach it. That started to change with two spacecraft launched in 1977, Voyager 1 and Voyager 2, originally sent out to tour the outer planets during a rare alignment that let a single mission fly past Jupiter, Saturn, Uranus, and Neptune, using each planet's gravity as a slingshot toward the next. Both spacecraft finished that planetary tour decades ago, but their nuclear power sources kept both machines alive and transmitting long after the last planet faded behind them, and mission scientists kept them pointed outward, chasing exactly this boundary for decades. If you're the kind of person who wants space stories explained clearly instead of buried under jargon, go ahead and drop a like on this video right now, because it genuinely helps this kind of content reach more people who would enjoy it. The first real sign that Voyager 1 was approaching something significant came years before it actually crossed the boundary. As the spacecraft pushed further from the sun, it passed through an earlier region called the termination shock, the point where the solar wind, having traveled for billions of miles, abruptly slows down from supersonic speed, as it starts running into resistance from the interstellar medium pressing back against it. Beyond the termination shock lies a turbulent, compressed region called the heliosheath, a kind of thick outer shell of the solar bubble where the slowed, bunched-up solar wind piles up against the boundary before finally giving way entirely. Voyager 1 crossed the termination shock in December of 2004. It would take another 8 years of travel through that turbulent heliosheath before it reached the true edge. That moment finally came in August of 2012, though NASA scientists did not announce it with full confidence until several months later. According to Ed Stone, the longtime project scientist for the Voyager mission at Caltech, confirming the crossing required more than a single instrument reading. The breakthrough came from an unexpected source, the spacecraft's plasma wave instrument, led by physicist Don Gurnett at the University of Iowa. In April of 2013, a burst of activity in the plasma surrounding the spacecraft caused it to essentially vibrate, and Gurnett's team was able to use that vibration to directly measure the density of the plasma around Voyager 1, essentially having the spacecraft sing a note that revealed exactly what kind of material was now surrounding it. The plasma density matched what scientists expected for interstellar space, far denser than the sparse solar wind inside the heliosphere, and dramatically different from anything the spacecraft had measured before. That measurement, combined with data collected months earlier, confirmed it. Voyager 1 had left the solar system entirely and become the first human-made object in history to enter true interstellar space, the region between the stars themselves. Voyager 2, traveling a different path at a slower pace, would not reach that same milestone until November of 2018, more than 6 years after its twin. But its arrival mattered enormously because Voyager 2 still had a working plasma spectrometer instrument on board, a sensor that had actually failed on Voyager 1 years earlier. That meant Voyager 2 could directly and immediately confirm, in real time, exactly what kind of plasma it had entered, giving scientists a second, independent measurement of the same boundary from a completely different location. more than 150 astronomical units away from where Voyager 1 had crossed years before. Here is where the story turns into something considerably stranger than a simple line being crossed on a map. As both spacecraft approached and crossed the heliopause, their instruments recorded something nobody had fully anticipated: a dramatic spike in temperature. According to data reported by NASA, instruments on both Voyager probes measured temperatures in this boundary region of roughly 30,000 to 50,000 Kelvin, somewhere in the range of 54,000 to 90,000 degrees Fahrenheit. For comparison, the surface of our own sun sits at roughly 5,800 Kelvin. The region just beyond the edge of our entire solar system was reading hotter by a wide margin than the surface of the star at the center of it. That discovery is exactly where the nickname came from. Researchers began referring to this superheated boundary zone as the Wall of Fire. It is worth being precise about what that temperature reading actually means, because on its own, it sounds like it should have vaporized both spacecraft instantly, and understanding why it didn't is one of the more genuinely fascinating parts of this entire discovery. Temperature, in physics, is a measure of how fast individual particles are moving, not necessarily how much total heat energy is available to transfer into an object. In the extremely sparse environment just beyond the heliopause, the actual density of particles is astonishingly low, far lower than even the thinnest laboratory vacuum achievable on Earth. The individual charged particles out there really are moving at blistering near-relativistic speeds, which is what produces that extreme temperature reading. But there are so few of them, spread across such an enormous volume of space, that meaningful collisions between those particles and the surface of a spacecraft happen only rarely. Without frequent collisions, there is no efficient way for that thermal energy to actually transfer into the metal and electronics of Voyager 1's hull. In effect, the Wall of Fire is blisteringly hot in the sense that its particles are moving incredibly fast, but it is simultaneously so empty that it has almost no ability to actually cook anything passing through it. That is precisely why both spacecraft could fly directly through a boundary, measuring tens of thousands of degrees, and continue operating normally on the other side, sending back data for years afterward. The second major surprise buried in this same region involved something scientists were watching for even more closely than temperature: the behavior of the magnetic field itself. Before either Voyager reached the heliopause, most researchers expected a fairly clean, obvious transition. The sun's magnetic field, which extends outward embedded in the solar wind, should give way at the boundary to a completely different magnetic field oriented in a different direction, one belonging to the interstellar medium beyond. What both spacecraft found instead defied that expectation directly. According to a NASA statement describing the finding, observations from Voyager 2's magnetic field instrument confirmed a surprising result, first reported by Voyager 1, that the magnetic field in the region just beyond the heliopause runs parallel to the magnetic field found inside the heliosphere. In other words, rather than an abrupt handoff from one distinct magnetic environment to a completely different one, the two fields appeared to line up with each other, at least in this particular region, suggesting the boundary is considerably more tangled and less clean than the simple diagrams found in textbooks had always suggested. For years, after Voyager 1's crossing, scientists could not be entirely certain whether that alignment was a genuine, widespread feature of the boundary, or simply a coincidence limited to the single location where Voyager 1 happened to cross. With only one data point, there was no way to know for sure. That uncertainty is exactly why Voyager 2's independent crossing, 6 years later, and in a completely different part of the sky, mattered so much. Because Voyager 2 measured the same parallel alignment in its own magnetic field readings, scientists could finally treat the finding as a genuine, consistent characteristic of this boundary region, rather than a fluke tied to one spacecraft's specific flight path. According to research associated with the Harvard-Smithsonian Center for Astrophysics, scientists studying this phenomenon have proposed that the sun's magnetic field lines may be getting stretched and dragged outward as the solar wind pushes against the interstellar medium, gradually reconnecting with the interstellar magnetic field itself rather than cleanly separating from it, a tangled gradual handoff rather than the sharp boundary many had originally pictured. Picture for a moment exactly what this region of space would actually look like. If there were any way for a human eye to observe it directly, because the physical reality is stranger than the word wall makes it sound, there is no visible surface, no shimmering barrier hanging in space the way the name might suggest. It is an entirely invisible transition zone, detectable only through the specific instruments capable of measuring particle speed, plasma density, and magnetic field direction. A spacecraft crossing it experiences no jolt, no visible event, nothing a human traveler could physically feel, and yet, according to the data both Voyagers gathered, the character of space itself genuinely changes there. The density of surrounding material rising sharply, the source of the particles switching almost entirely from solar in origin to interstellar in origin, and the temperature of that sparse material spiking dramatically, all within a relatively narrow, if still poorly mapped transition region. Some researchers who have studied the crossing data describe it less like walking through an open doorway and more like stepping over an unusually abrupt threshold, given how quickly certain readings shifted as each spacecraft pushed through. If you have found this as fascinating as I did while researching it, drop a comment letting me know, because it genuinely helps me figure out what other space stories are worth covering next. There's a broader mystery tied up in all of this that researchers are still actively working to understand, one that reaches well beyond the heliopause itself. Because the heliosphere is not simply sitting still in space. Our entire solar system is moving through the galaxy, carrying that enormous bubble along with it. Some researchers have proposed that this motion should produce a bow shock ahead of the heliosphere, a region of compressed, turbulent space analogous to the wave that piles up in front of a ship's bow as it cuts through water. Whether a true bow shock actually exists in front of our solar system, or whether the heliosphere instead glides through the surrounding interstellar medium more smoothly than that model predicts, remains a genuinely contested question among researchers studying this region, one that data from both Voyager probes has only partially been able to settle so far. There's also the question of overall shape. Early models generally pictured the heliosphere as a long, comet-like teardrop with a rounded nose facing the direction the sun travels through the galaxy, and a long trailing tail stretching out behind it. More recent modeling work, incorporating updated data from both Voyagers, alongside observations from NASA's IBEX spacecraft, which studies the boundary indirectly by detecting particles bouncing back from it, has suggested the true shape may be considerably more compact and rounded than that classic teardrop picture, closer to a deflated croissant than a long comet tail, according to some of the researchers who have modeled it. This remains an active area of ongoing research, and different modeling teams continue to arrive at somewhat different conclusions, depending on which data sets and assumptions they build their simulations around. It's worth taking a moment to appreciate just how much of a technical miracle it is that either spacecraft is still returning data at all, roughly 50 years after launch, to make any of this possible in the first place. Both Voyagers are powered by radioisotope thermoelectric generators, devices that produce electricity from the natural decay of a chunk of plutonium loaded onto each spacecraft back in 1977. That power source cannot be refueled, and it has been steadily declining ever since launch, forcing mission engineers to switch off instruments one by one over the decades simply to keep the remaining systems powered and communicating with Earth. Both spacecraft are now traveling outward at somewhere around 38,000 to 35,000 miles per hour, and radio signals from Voyager 1, even moving at the speed of light, the fastest velocity anything in the universe can travel, now take more than 23 hours to reach ground stations back on Earth. Every single piece of data described in this video had to cross that entire distance, one full day's journey at light speed, before scientists on the ground could even begin to analyze it. It is also worth being honest about exactly how much remains genuinely uncertain about this entire region of space, because that uncertainty is precisely why scientists remain so invested in every scrap of data these aging spacecraft can still provide. Both Voyagers carry a limited aging suite of instruments, several of which have already been permanently switched off to conserve dwindling power, and each spacecraft only ever crossed the heliopause at a single specific point, meaning researchers are essentially trying to reconstruct the shape and behavior of an enormous, three-dimensional boundary using data gathered along only two separate paths through it. Every new measurement either spacecraft manages to send back, for however many more years its power supply allows, remains one of an extremely small handful of direct data points humanity has ever collected from beyond the edge of its own solar system. So, what does all of this actually add up to? For decades, the heliopause existed only as a line on a diagram, a theoretical boundary calculated from physics, but never actually touched by anything humanity had built. Two spacecraft, launched in 1977 on a mission originally expected to last only a few years, eventually reached that boundary anyway, flew directly through a region measuring tens of thousands of degrees, discovered that the boundary itself behaves nothing like the clean edge scientists had expected, and kept going, sending back data from true interstellar space that no other instrument built by human hands has ever directly gathered. It is not, in any literal sense, a solid wall. There is nothing there that could stop a spacecraft, or trap it, or hold it back. But in every sense that matters scientifically, it is a genuine boundary, a place where the character of space itself fundamentally changes, measured directly for the first time in human history by two machines that were never supposed to still be running by the time they got there. Here's the detail that tends to stick with people longest once they hear the whole story laid out. Somewhere right now, more than 14 billion miles from Earth, in a region of space this hot and this empty at the same time, Voyager 1 continues drifting outward, carrying a golden record on its side containing greetings, music, and sounds from a planet it left behind nearly 50 years ago, still occasionally sending back faint signals from a boundary most people didn't even know existed until a handful of scientists spent decades waiting patiently for a 50-year-old spacecraft to finally reach it. If stories like this one, grounded in real published research rather than exaggerated headlines, are what you want more of, subscribe to this channel and turn on notifications, because both Voyager probes are still out there, still transmitting, and there's a real chance the next signal that reaches Earth adds another genuinely strange piece to a boundary scientists are still working to fully understand. Thanks for watching, and I will see you in the next one.